Hello and welcome to our second retrofit in our series Eco-retrofit for householders. This one's on air tightness, and I'm really pleased to have Diane Hubbard of Green Footsteps, who is our resident expert in Cumbria on air tightness. The agenda for this evening, I'm going to do a short welcome and introduction, then I will hand over to Diane for her presentation, which will take about 40 minutes. Then we'll have about half an hour for Q&A. So do think of questions as you go along, drop them in the Q&A. And finally, we'll have a poll and just a wrap up at the very end. And we should finish promptly at 8:30. So for those of you who don't know about CAFS already, I would encourage you to go onto the website and look at the projects that we do. We cover all sorts of things, not just energy in homes. And we are involved, we are co-chair of the Zero Carbon Cumbria Partnership. So we're doing all sorts of different things across the whole of CAFS. And just a quick plug for our Christmas gift cards. 4 of our projects at CAFS are being supported this year with a lovely gift card. So do go and have a look at our online shop on the CAFS website. I want to tell you a little bit about the CAFS energy services. They divide roughly into free services and paid for services. So on the free side, Cold to Cozy Homes provides help, some just free help for anyone, but some help is based on whether people are eligible or not. We also offer webinars like this for free because we've got funding to do so. And our paid for services, we always start with a free consultation by phone and a quote. But if you're interested in more in-depth advice, then we've got our Home Retrofit Planner report. And we also are running extra services, which we're piloting at the moment, and looking to extend the help we can offer through the retrofit process. I mentioned the Cold to Cozy Homes. So this is for people who want common sense energy advice and different eligibility criteria. It's quite broad. Don't just assume you wouldn't be eligible. And now we are also starting to look at retrofit advice in there, particularly for people who might be eligible for energy saving measures under government schemes. To just explain a little bit about our Home Retrofit Advice Service, the main starting point is our Home Retrofit Planner, which is an energy model. It helps you look at your home energy usage, your carbon footprint, helps identify the improvements you might want to make. It's a decision-making tool, and it can look at different scenarios compared to what your house is like now. And then the other services that we are starting to offer take you through the design process and then on to finding installers. Also, just to say that we are running a project called Retrofit Made Easy at the moment. So if you're interested in retrofit and you'd like to come along to an in-person event, we've got events in 4 different parts of Cumbria across January and February. They're all detailed on the CAFS website on the events page. And in those communities, we're doing thermal camera surveys with community volunteers. So if you live in one of those listed communities, you can get in touch with the community group. Just go to thermal imaging, search it on the CAFS website, and you can book directly via a community group. And that might be something of interest for some of you. And in those communities, we're doing some peer group support around retrofit. Also, our Solar Made Easy project is running across the whole of Cumbria. Doesn't matter where you live in Cumbria. It's about independent advice and getting quotes from 2 of our local vetted installers. So if you're thinking about PV panels, that's something you might want to look at. So Diane. Diane is a mechanical engineer with a background in building physics, and who's done the Masters at the Centre for Alternative Technology, and has been working as Green Footsteps for some years now. And this involves air tightness testing, often with infrared thermography, and carrying out energy calcs for new builds and for retrofits. And she's a passive house consultant, tradesperson, and has other qualifications in ventilation. So we're really very lucky to have Diane come and talk to us. And she's got a lot of hands-on experience of doing air tightness testing in homes, and that's what we're going to hear about now. So over to you, Diane. I'll stop sharing my screen, that might help.
Yes, that would help, yeah.
I'm just going to answer two questions in the, okay, so this is great. We've got a few questions already coming in. So that's great. Keep the questions coming in, and when Diane has finished her presentation, we'll go on to those questions.
Okay, you seeing the screen all right?
Yes.
Great. Okay. Yes. So that poll's really useful because it gives me a much better idea of who I'm speaking to. I also recognise a couple of names. So hello there, people I know. Yes. So this is really pitched at the sort of starting point. Okay. I'm sure that when we get onto the questions, and it's great that we've got a reasonable amount of time for the questions at the end. I'm sure we'll get into more complicated issues. But how I've pitched this is really to try and go through the basic items and make sure we've got those covered, because sometimes there's an assumption that, or maybe misunderstanding. So it's important that we recap on those as well. So Tina's already sort of given some background on who I am really. Just sort of covering things in a bit more detail. So my background in terms of my interest, my research area is older buildings, pre-1900 buildings, and looking at sort of what happens in terms of occupancy and ventilation and moisture. So that's what my core, well, I wouldn't say interest, but that's where I've my research is really focused. And I sort of got into all this a bit by accident, really. I live in a stone-built house, and at the time when I started the Masters at the Centre for Alternative Technology, nobody could really tell me what to do with it. So that was one of the drivers in actually looking at it. So over a period of time, I've sort of identified where there's a bit of a hole in either my knowledge or general knowledge, and I've then trained to sort of expand my knowledge. So for example, on the passive house side of things, the reason I did the training to become a passive house consultant was because what I could see was the principles of passive house could be applied to existing buildings, basically. So things like design it properly before you start and carry out quality assurance through the process really sort of resonate with my background in engineering and thinking we should be approaching this more systematically. So there is a logic behind that progression of various things on that list. The ventilation side is there because if you're looking at airtightness, you really have to make sure that ventilation is taken into account. And that's going to come through when I start going through the slides, really. Okay, so what are we actually talking about when airtightness? I think the thing to think about first is infiltration is what we're really talking about. And as it says on the slide, infiltration is about the uncontrolled flow of air through all those little cracks and crevices and things within a building. So uncontrolled is the key thing. It's something that is driven by maybe temperature or wind, and we just cannot control it. So it's unwanted stuff, and we have to differentiate between that and ventilation, which is deliberate, which we actually need within the building. So that's what we're talking about. We're talking about infiltration, and it's important to make that separation. So when we're thinking about sort of air quality, people say, well, I live in an old house. I like ventilation, right? So I don't want to bung up all of those holes. The thing to bear in mind, I mean, you'll see that the diagram on the left-hand side is an expanded version of what I've just shown. But for example, if you want to ventilate the house by infiltration, what you're talking about is air coming from spaces which is not really where it's designed to come from necessarily, like under the floor voids or through the insulation in the loft, or there are question marks over the quality of that air that comes through there. And is that what you really want in terms of how you ventilate your property? So it's really important to differentiate between infiltration, this unwanted stuff, and deliberate ventilation, which is usually usually fresh air from outside through a reasonably clean route, which it isn't always with infiltration. The other thing I'd like to make clear, the other thing that comes up so many times, and Tina probably knows I get really upset about this one, is people get confused between infiltration and breathability. They say, but the building's breathable. And in terms of definitions, it's important to understand that when you're talking to somebody, whether it be an architect or a surveyor, and they use the term breathability. I'm talking to you as householders, by the way. I don't know how many of you are builders out there, so I'm really talking to you as a householder. Breathability isn't anything to do with airtightness, right, or infiltration, right? Breathability is about moisture. Okay, it's the ability for vapor to travel through building fabric. Nothing whatsoever to do with airtightness or infiltration, but it's very easy to get confused. So that word breathability, at first bit, well, it's really not great in terms of terminology. So really what you should be thinking about is to replace, don't use the word breathability, because it's something that we can easily get confused about. It's actually vapor permeability is what we're talking about, where moisture can travel through a building fabric. Particularly, it's used in relation to older buildings which have materials that have been used historically, really. So things like lime or clay. So I just wanted to get that terminology a little bit clearer. So back to infiltration. Okay, so airtightness is basically infiltration quantified. Okay, when we're talking about airtightness, it's all those leakage points, and what does that actually equate to is what we're talking about. So what we've got on this slide is, you can see that we've got a blower door on somebody's front door, happens to be a listed building, and what we're trying to do with the airtightness test. So this is a blower door test. You either pressurize the building using that fan that's in the door, or depressurize it compared to outside. We do that to 50 pascals difference. That won't mean anything really to you. It's the equivalent of a wind speed, the pressure applied by a wind speed of between 20 and 30 miles an hour, basically. And what we've got on the right-hand side is a couple of typical images we might see with a thermal imaging camera when the building is depressurized compared to outside. So the top image on the right-hand side it's a wall floor junction, and what we're seeing is those cold fingers are actually air, because the building is depressurized. It's pulling the air through the building fabric, through the crack where the wall hits the floor, pulling the air through there, and that's what those cold fingers are. It's not the air we're seeing, it's actually how the colder air is cooling the surface, the floor surface, and there's some actually going up the wall in this instance, but that's what we're seeing. We're seeing the cold fingers of air. So in order to carry out this test that is occurring on this particular building, we've got the building heated inside compared to outside. So this sort of test is usually done in the winter. And what it enables us to do is to compare different areas of the building and see how important, relatively speaking, things are. Is it the front door that's leaking? Is it the back door that's leaking? How much roughly? Which is the worst one? If you can afford to replace one door, which one do you do? How does that compare to what's happening at the floor? We can really do a very good comparison. And the thing with thermography under normal conditions is that you're seeing primarily where there's thermal bridges, and they're quite predictable in existing buildings. Unless you've got the wind blowing while you look at it with thermal imaging camera, you won't see patterns like this under normal conditions. It's actually the depressurization that gives that pattern. So the lower image we've got there is of a loft hatch. So classic sort of frame around the loft hatch and a board sitting on top of that frame. Okay. And what we're seeing again is those cold fingers of air. The darker patches are the lower temperatures. The temperature itself is given by the scale on the right-hand side. And we can see how much air is coming in around that loft hatch, with, again, the building depressurized. So what's actually happening is the fact that the building's depressurized, it's actually pulling the hatch down into the frame. So this is like the best case of what this is going to look like. Under normal conditions, what would be happening is that would be lifting slightly because of the way that the pressures work within the building. And so it would actually be slightly worse than that. But it's great because the images then allow us to sort of, as I say, compare different areas of the building. And it's great to be able to make something tangible that's quite difficult to relate to. Leakages like this you'll be able to feel, but you know, the hatch is up on the top of the ceiling. You can't necessarily put your hand up there. You could feel it at the skirting boards or at the floor wall junction, but it makes it visible and it makes it recorded so that you can then look back at it at a later stage. So that's what we're talking about in terms of, okay, how do we measure air tightness? We normally do it with a blower door. And how do we investigate what's happening? It's great to use thermal imaging. Sometimes I'm using smoke, but thermal imaging is great to use in that instance. So why is air tightness actually important? Why are we bothered about it? Okay. So everybody, the one that isn't on this list is it affects your comfort. You know, you are sitting in your living room and you get drafts around your ankles because the door is a bit leaky. Okay. So what I'm talking about here is let's think about the things that aren't necessarily that obvious, because it goes much wider than that. So first thing is, if you've got lots of infiltration, then it's going to impact your energy use. It will, you know, how much depends on how leaky it is, or depends on as well how energy efficient your building is overall. So if you've got a good level of thermal efficiency in the building, if you have relatively poor air tightness, it can really mess things up. So it's difficult to put exact numbers on it. You know, I mean, we've looked at particular case studies where you can see that when you're getting down to reasonable levels of air tightness, you know, if you're looking at, say, the difference between 2 and 1 with good levels of thermal performance, you're talking about a major amount of energy you're potentially saving, because you've got simply less air going through the building, you know, that's uncontrolled. So it's building specific how much it's actually going to save you, but it can be a major contributor. Even though air is actually relatively easy to heat, you know, it can be quite significant. Another thing that people don't really think about is thermal bypass of the insulation. Now, what I'm talking about there is if you've got insulation fitted and there is air going through it or around it, it's not going to perform the way it was intended. So a good example is that if you have, say, some rigid insulation, for the purposes of this, we'll just call it Kingspan. Other insulation materials are available, but say you've got some Kingspan fitted between 2 bits of timber in your loft. You're using that at the joist level for insulation. Now, the thing is, the timbers wander a little bit, okay? And maybe there's a bit of debris on the plasterboard ceiling that's holding the insulation off a little bit. The air will circulate around that insulation, and what will happen is it will severely impact the performance of it. So avoiding thermal bypass is really important. So what we're talking about there is things like removing air voids, making sure things are a really good fit, making sure the materials are appropriate. So maybe rather than using a rigid material, something that can be like squashed into place a little bit. So it's a really good fit, so you don't have air gaps down the side. So it can be a significant contributor. And often when I'm doing tests, like the images I've just shown you before, I have some really good examples of insulation that's being bypassed completely. And, if it's bypassed, is it really worth it being there? Or if it's not performing in the right way, in terms of carbon impact, if you're not seeing the benefit from it, you've spent that money on insulation, we really need to make this stuff work, basically. Another thing about airtightness is if you've got relatively poor airtightness, there's a risk of moisture ingress into the building fabric. Now, the one that springs to mind immediately is sort of newer timber frame buildings. I mean, for this presentation, we're talking about retrofit primarily, but if I can just drift off into that for a moment. And if you've got air that's leaving a nice, warm, heated space that you live in, and it's finding these infiltration routes through a timber frame, at some point that moisture is going to condense on its way through as it goes out to the colder environment outside. That condensation is then a risk to that timber, and it will potentially shorten the building's life. Thinking about it more in terms of, say, a retrofit, if you're, say, used timber studs on, maybe you're applying internal insulation and you've used timber studs, and the air tightness is not great on that, there is a similar risk because you've got timber there again, and the air is cooling as it goes through. So again, you're potentially risking either the life of what you've done, or there's a mold, there's a mold risk, really, because if you're talking about significant humidity levels. So from a health point of view, it's not great either. So the risk of moisture ingress should be viewed really seriously in retrofit. The other thing to bear in mind is ventilation system performance. And primarily what I'm talking about there is where you're looking at quite good levels of air tightness, and you're maybe looking at a ventilation system such as a mechanical ventilation system with heat recovery, MVHR. And if the building itself is quite leaky, then an MVHR is usually well designed with defined air routes through the building, so that you're putting air into your main living spaces, bedroom or living room, and you're extracting it from places like the kitchen and bathroom. And the whole thing relies on these air routes working properly. If you've then got, say, a leaky bathroom, that's got poor air tightness, what's going to happen is the air will come from the easiest route. So it won't actually travel from the bedroom that's next door. It will actually just come through the wall. And so you're potentially not getting the right ventilation routes, and that air is then potentially cooler. And so in terms of heat recovery, it messes things up quite a lot, really. Ideally, I mean, you really want the building as airtight as you can get if you're looking at things like mechanical ventilation with heat recovery. Okay, so if we talk a little bit now about quantification of infiltration, so air tightness, what are we actually talking about? I've mentioned already, do it through a blower door test. The picture here I've got is of a test that I did on it's a non-domestic building, just using 2 fans, so just a slightly different setup. And the way that I do the test is I basically prepare the building as if it was a new build building. So in the same way that they're tested, so that when we're looking at the results, we've got something that's comparable, so that we can draw comparisons between your home and the new build house down the road or a passive house. We can make a comparison. If we don't have that common base, we're not comparing like for like. Now, the next thing people say is, but I've got an open fireplace. And I understand that. What we're trying to do with the blower door test is we're trying to look at the things that you can't control. If you have a fireplace with an open flue, that's something you can actually do something about. So we treat that as a separate thing. What we're trying to do with the test is look at what's your actual underlying building fabric like. So that's the reason they're covered over. It's so we can compare things directly with a new build test. So you'll see that there's two ways that people actually refer to airtightness. Okay, they talk about something called air permeability or air changes per hour. Okay, and sometimes it's not clear. Okay, people will talk about airtightness, and they may not know what they're talking about. You have to bear that in mind. So the easiest way to know what they're actually talking about is to ask them what the units are for what they're talking about. And they might not know that either. Okay, but to try to get to the bottom of what they're talking about, ask what the units are. So the first one I'm going to talk about is something called air permeability. And in the UK, this is what we work to. Okay, air permeability is what's in Part L of the building regs, that looks at the energy of buildings, and Part L for new builds specifically. There's no requirement to test existing buildings whatsoever. Okay, but air permeability is the most common thing in the UK, and what that basically is you've got the flow rate that the fan delivers. That's meters cubed per hour compared to the dwelling envelope. So that's the lowest floor, up the walls, top of the highest ceiling, right? It's basically the extent of the thermal envelope of the building. The other thing that does come up, which is actually easier to relate to be honest, is air changes per hour. So that's how often the air in the building changes per hour. I suppose it does what it says on the tin, really. So what we've got is the fan flow rate again divided by the volume of the building. Now, the definition of that volume can be a bit more complex in some instances. So we start talking about passive house. There's a very specific definition. But that's really, for you to look into in a bit more detail. But broadly, we've got those two things, air permeability and the air change rate, the air changes per hour. It's all done at the same pressure, 50 pascals pressure difference. Okay, so does it actually make any difference if we're talking about air permeability or air change rate? The answer to that is it depends, okay? Because if you've got a building like the building on the right, this is actually the home of somebody who does quite a lot of retrofits locally, but in itself, it's a new build. If you've got something boxy, right, very cuboid, then they're very similar, okay? But if you've got an L-shaped bungalow, like the one on the left-hand side, they can be very different because that's got quite a big surface area for the volume. So sometimes they can be very different figures, and you need to bear that in mind. The thing about air permeability, so relating it to the surface area of the building, is quite good because it's a function really often of the easy flat stuff. The flat stuff is easy, right? The difficult bits are the junctions. And in something like an L-shaped bungalow, you've got lots of junctions, okay? Whereas if you've got something like the box on the right, that's basically designed to passive house principles and has a minimum number of junctions, a minimal amount of complexity. And that's why when you look at passive houses, new build passive houses, you'll find that they are really straightforward in terms of form. And that is to make it as easy as possible. So it can make quite a difference. There can be quite a difference between the two sets of figures, air permeability versus air change rate. Okay, so what I'm going to go through here is to give you an idea of, okay, well, what we're actually talking about in terms of numbers. Okay, so these are sort of typical benchmarks that you'll come across. Okay, so if we start at the bottom and work up, the thing to remember is the lower the number, the more airtight it's becoming. Okay, so as I mentioned before, I like to draw parallels to new build, and I think that's a valid thing to do because it allows us to set a scale on what we're talking about. So the current limit on new builds is an air permeability, so that's the units meters cubed per hour per meter squared at 50 pascals. So 8 is the limit for new build dwellings in the UK. In reality, though, it's rare that you're able to go that loose. Typically, if you're sort of thinking of a 3-4 bed detached major house builder type house with gas central heating, they've probably got to hit about 5 at the moment. Okay. Then some of you might be familiar with the AECB level 2 retrofit standard. Okay. Now they're working to an air permeability on the retrofit standard, and you have to come in at under 2 on the to achieve the AECB level 2. You may have also come across ENERFIT, which is you have to come in under 1. Now you'll see there's a unit change here because it's a different methodology, and ENERFIT and both ENERFIT and new build passive house works with air change rate at 50 pascals. As I say, it's defined slightly differently from how it's a slightly tighter volume figure, but for the purposes of this, we're just comparing them, and we'll assume it's a bit of a boxy house we're looking at, so we just make comparison, between, look at those figures. So you can see the progression there, that compared to say what we're building as a new build house now, typically, you're looking at quite good levels of airtightness that are needed in order to get these 2 key retrofit standards that we're looking at in the UK at the moment, the AECB level 2 and the passive house standard. Now, I'm not presuming you have a standard in mind, okay, but it is worthwhile having a benchmark, an objective, because one of the things I find when problems occur, whether that's new build or retrofit, is when people don't have a defined standard, a defined objective that they're trying to work to. So think of where you want to be. That's going to be defined by a whole series of factors, and that's what the rest of the presentation's about. But you need to, it's a really good idea to have a clear objective of where you're trying to get to. So the next question, I would think that if people could ask questions at this point, what they're likely to be asking is, where is my house likely to be to start off with on this scale? That's an interesting one, because I thought when I first started to test existing buildings, I thought, oh, there'll be a pattern I can find, okay, in this. Sorry, guys, right? It's not that straightforward, because it really depends on what's been happening to the building. So in terms of where it could be, it could really be all over the place. I have tested all sorts of buildings. I find that, well, there is, in terms of what is we're generally aware of, there was a study done quite a few years ago. Base data is a bit questionable, but I do refer to it. And that comes out in air permeability, an average sort of in the UK, going back quite well. So not really in-depth retrofits in there, but a baseline of about 11.5, an air permeability of about 11.5 was about where the average was. Okay. So I tend to compare things to that. I've had buildings that have been miles over that way and miles over that way. So I've had buildings that have been 100 years old or 120 years old that have come in at 5 as an air permeability. I've had buildings that were built in 2015 come in at 35. Okay. It is quite shocking, the range. Okay. I did a test today. Poppy, if you happen to be on this, I didn't see your name, but I did a test for somebody called Poppy this morning on a early 1970s at a Guess semi with solid floors and wet plaster on the walls in, I have to say, mint 1970s condition, complete with glass blocks and sort of anaglypta. And it was, that came in at about 7.5. But there could be, if that had maybe had an extension on it, it could have come in completely different. Okay. So it's really difficult to know where your home is without testing it. And I'll go on now to explain why. Okay. So hopefully that's set a bit of context for you. Okay, now I need a bit of audience participation. Okay. I want to know, we'll do the worst one first. I want you to put in the chat. We're not chatting, are we? It's questions. Okay. Okay, you have a minute to decide. First of all, I want to know which you think the best one out of all of these properties is. And then I want to know what the worst property is. So first of all, 60 seconds on what the best property is, best air permeability. I've only seen one answer so far. Is that all? Is everybody else thinking? 2? Okay. Oh, somebody's raised a hand. Okay, come on, somebody else comment. Is that it? Okay, right. Okay, drawing a line under that one. So what gets the vote then, Tina? I can't hear you. You're going to have to come on mic.
Yeah, we've got quite a range. We've got best top right.
Sorry, could you say that again?
We've got top right, middle, bottom right, lower left or right, top right, bottom right, top left. We've got a real good range. I think we've hedged our bets.
Yeah. Okay. Right. Okay. Should we? I think we'll let's try the worst now. Okay. Right. So you got 60 seconds to put the worst one in the chat. Which do you think is the worst?
Actually, someone's raised their hand. I'll briefly allow them to talk. Hello, would you like to, have you got a question that you've raised your hand? I think that's Sandy.
Mute. Could you come off mute, Sandy?
Yeah. Can you hear me?
Yes.
I raised my hand by accident.
Oh.
Sorry about that.
That's all right. No trouble. What we'll do is we'll go back to the answers.
Was that to get out of answering the question? Can I just ask?
No, I've I've already muted him. Sorry.
Okay. Right. Okay. So what's the picture on the worst?
Again, mixed top left, middle, top right, middle, top left, castle, worst, middle. Lots of people think the middle one is the worst, the castle.
Okay. Right. Okay. So that's very interesting. Okay. So I'll put you out of your misery. Okay. So the best one that's here. So we've got clearly that the The three on the left-hand side are all existing properties, you know, older properties, some older than others, 1503 the castle, by the way. And on the right-hand side, we've got two new builds, okay? One is a mass developer, and the other one is sort of a small group of, it's a small group of buildings by just a local builder. Okay, so putting you out of your misery, it's quite a close run thing as to which one is actually the more airtight. Okay, in terms of air permeability, the best one is the bottom left. Okay, which is built in the late 19th century. So it's the brick one on the bottom left. It's only very, very slightly better than the one on the bottom right, the new build at the bottom right. Okay, so they're the best. Okay, the worst is this lovely 1930s semi. Okay, so I'll put some numbers on these. So that the 1930s semi was came out at just under 15 as an air permeability. Okay, the castle came out at 12 in terms of air permeability. Okay, and the mass house builder came out at just under 5. Okay, so so you know, you can't always go on what it looks like. Okay, in terms of where it sits. So the castle is only slightly worse than the UK average for dwellings. Okay. So yeah, but as I say, I've had ones that are buildings I've tested which are a lot leakier than those. But it does. You really have to start to don't assume is a key thing about when you're looking at airtightness. Why was that not?
I think it's a bit slow sometimes changing the screen. Lovely.
Let me just check I've not done it. Yes, okay. Right, okay. So when we're talking about airtightness, the most important thing to realise is that common building materials let air through. Okay. So brickwork, blockwork, stone walls, they all let air actually permeate through them. So when you've got when the wind blows, or when we're running an air tightness test, depressurized, air will come through walls. And that's quite a shock, really, particularly to builders on occasion when you're testing a new build, and they say, no, it doesn't come through. And then you take them to a location where they've got some open block work, and you say, put your hand on there, and you can feel it coming through the block work. So the thing is that in older buildings, the thing that stops the air movement is the plaster that's on the inside. It stops it from actually getting through into the inside of the dwelling. So when you're starting to think about air tightness, you have to think about those areas where either there's no plaster or the plaster is broken, because they will be the key points where you're going to get this infiltration, this air ingress. Okay, so I've got a couple of images here that hopefully illustrate it. And again, Poppy, please excuse me if you happen to be in this group, because I haven't sent you these images yet, this top image that I took this morning, but I thought it was such a nice image to compare it to the one below. Okay, so what we've actually got here is two separate buildings. Okay, so the one at the top is this 1970s semi, which has wet plaster on the walls. And the one at the bottom is a new build that I had to test. They were having problems with actually keeping the building warm. Okay, and the key what I'm trying to show with these images is the impact of plaster, really. So the view on the left hand side with the thermal image is just that central bit of the daylight image on the right hand side. So we're looking in this area here. And what we've got, we've got those telltale sort of fingers going along from behind the coving. There's a bit of a crack in the ceiling there. And you can see that there's some air is coming in there. The building, in both cases, the building is depressurized compared to outside, so it's under my test conditions. So we've got a bit of air leakage coming in there, but we've actually got quite a uniform appearance on the walls. We can actually see the blocks. The building is constructed of concrete blocks on the inside, and then it actually has a brick outer leaf, but it's concrete blocks on the inside. But we've got it's quite uniform. Okay. When we look on the image below, what we've actually got is we've got the most common thing that people do when they're either retrofitting or basically is a standard method for how we build our new builds, which is plasterboard fixed on dabs. So it's dot and dab plasterboard. Now, when you look at all of the plasterboard manufacturers, they say the plasterboard needs to be edge sealed. It's around the perimeter of each board. When it's fitted, it should have a continuous line of adhesive that would seal around the perimeter of it. It's very rare that I actually see that when I'm testing a building. And this example is it's in a bedroom, and what we can see is we can see the dabs that are holding the plasterboard onto the wall here. That's what the warmer coloured things are. And what we've got around that and going way down the wall, so we're talking about down to here on this right-hand image, we've got all this cold air coming in from the attic, bypassing the insulation in the walls and affecting the performance of the building. Okay, it's under test conditions, so in reality it might be going in a different way, but it's not it has a route for bypassing insulation. So when you're starting to think about a retrofit, you need to think about what you're actually doing in terms of how you are creating an airtightness layer. In your home, I'm assuming it's an older building, it's probably wet plaster. If you're getting somebody to do the work, they will be assuming they are going to be, a normal builder or normal contractor would be assuming that they're likely to use dot and dab plasterboard on the works that you're going to want doing. So you've got to be really careful that actually you don't make the situation worse in terms of airtightness with the measures that start to be put in. So, and I see the issue below really commonly in retrofits when I'm examining it afterwards, or after major building works and things. That's a really common situation to see that being bypassed, the insulation in the wall being bypassed. So how are we going to actually achieve airtightness? So I tried to break it down into a few steps here, and I'm just going to talk them through. Okay, so from my point of view, I'd say you need to know where you're starting from. You're probably thinking, she's bound to say that, she flogs tests, right? But the reason I do the tests is because I see a merit in doing it, because you need to know what you've got. Again, an engineering approach, right? You can have a goal for your project, but if you don't know what you're starting from, you aren't going to get to where you need to be, okay? So knowing what you've got is really important, and it's even more important if you've got a very tight budget that you're working to, where you know you cannot do everything to that building, and you're trying to work out, what am I going to get my best return on the basis of doing? So knowing where you start from. Okay, so what we're talking about there is a combination of putting a number on it, so you know roughly where it sits on this grand scale of airtightness. Have you got a dead leaky building? Have you got something that's actually about all right? So like the test I had this morning, actually, she was really chuffed that she got a decent, she got quite a respectable level to start from. That was really helpful to her. She was worried about it beforehand. It's going to be really leaky. But actually, that was she got a reassurance. Sometimes it goes the other way, right? Sometimes I have had situations where, you test the building, and really the key recommendation is, when are you thinking about moving, right? Because actually there may be so many issues with it, it might just be too difficult to sort out within the budget that you've got. So sometimes I'm doing these tests before people buy their properties, you know, alongside, you know, the survey reports and everything that they get. I do, you know, people check it out before they actually buy it sometimes. So that's actually quite I think that's quite sensible, but you know, you may not be in that position. Okay, so examples of what we've got here. So this building, in terms of numbers, I think it was about this had an air permeability of, I think it was about 20. Yeah, it was definitely the wrong side of 15. I think it was about 20. And you've got a building that it's a barn conversion from the 1990s, and they stuck there's two extensions on it, which the householder had been there a number of years, and they've done what is the orangery and the kitchen, which is the building, the extension on the left-hand side of that photograph. And this particular picture is taken is the ceiling of the kitchen extension, or part of the ceiling of the kitchen extension. And, you know, the starting point for this was the occupier says, well, we've either got to do something with it or we've got to move, right? We have to address this because we cannot afford to heat the building any longer. And the test highlighted a serious major thing, which was basically a blooming great hole near where the boiler was. But this specific thing that we're looking at in this image, we can get quite a lot from this. So the ceiling is sort of, it's a part sloping ceiling, and then we've got an inaccessible void over the main part of the kitchen. Got lots of air leakage along a beam here. We've got areas where there's no insulation, or doesn't appear to be insulation in the ceiling. So that one image tells us an awful lot. So that's an example of what you know, where you might be starting from. Here are a couple of other examples. So this is in a test from last year, where a lot of the issue often relates to services, where you've got waste pipes going out, you know, water pipes moving around the building, that sort of thing. Again, this is done under depressurization. So we've got those nice air trails, and you can see it's almost like a waterfall of cold air down the side of the bath, as the air is coming into that space under the bath and around. And that client's now sorted that issue out. They've sort of remodeled that bit of the building because they were having problems actually keeping that bathroom warm. So that's another example. So understanding what you've got, that's what the test does. It tells you where you are on the scale and what the issues are, and roughly which the more major ones actually are. Okay, so the next stage after that is you've got to decide what you're aiming for. What's your objective? Okay. Now that's going to depend, you know, how much money you've got, what your objectives are. You know, are you looking in terms of carbon? Are you trying to just simply get the energy use itself down? So that's up to you, the client, to decide what your objective actually is. But from a combination of baselining the building and then your objectives, you develop a strategy. Now, sometimes that strategy is developed by, you delegate that to, say, an architect. Sometimes you'll be doing it, you know, you might choose to do it yourself. However it happens, it's got to be designed in from the beginning, okay? So don't feel like, okay, I'm going to sort that particular problem out at this moment because there might be unintended consequences from doing it. It's really important to think it through completely before you start, so that you're not having to then revisit things. There's a cost implication of that. There's carbon implication of that. It's a waste of your time. So designing it in is a really important stage, and you have to spend significant time on that. And it's not all about fancy materials. I've talked a lot about wet plaster so far. There are some fancy materials you can use. I'm sure there'll be some questions come up on fancy materials. I have a selection of fancy materials here to talk about later when we talk about questions, but it's not all about that. Again, this house that I showed you earlier, the whole principle, I realise this is a new build, but it was constructed on the principle that everything had to come from Travis Perkins apart from the windows. Okay, the windows came from somewhere else. But basically, the builder had to get everything through the normal sort of routes. So you've not got to, it hasn't necessarily got to be all about doing something with these fancy materials. There are lots of things that you can do with basic materials. Okay, so what do you do? How do you design and develop a strategy? Okay, so what you do is you basically look at your building, whatever form that is in, and you say, where is my air tightness layer? And you literally take a red pen and you draw around the building, and then you think about the points where the air tightness layer either has a junction, so the things where the red dots are on this screen, yeah, or where you've got points where things are going through that air tightness layer. And you then need to think about how those are being dealt with. The first thing is, can you reduce the number of them? So a classic example is light fittings, okay? And, you know, I'm sure we've all been into properties where there's like tens and tens of inset light fittings. And if that ceiling is is actually your air tightness layer, every light fitting is going through it. So thinking about how the light fittings are mounted, what's the choice of those, or whether there's a way, if you want inset light fittings, can you create a service void so that the air tightness layer isn't breached, even if you use those light fittings. So really thinking it through in 3 dimensions. So you have to think about every time it's going to be broken, or when it joins something where it changes direction, and how that is dealt with. That can be quite painful, but having gone through that process and thought it through, when you come to implementing it, it becomes more straightforward. And really, if you're if you have subcontracted doing this to an architect, you know, if you've got an architect engaged, or, you know, even if you're, you know, if the builder is saying, yeah, I can do air tightness for you, go through this process yourself so that you understand it and you understand what you're actually asking for. And so think it through yourself as well. Okay, so how are you going to achieve it in terms of actual implementation? Okay, so this is written from the householder's perspective. Okay, so the number one thing on my list is you need to clearly convey what your objectives are, whether you're talking to yourself or whether you're talking to somebody else. So understanding what you are trying to achieve, so that, you know, if you're just trying to get to a moderate improvement, that's a completely different approach to if you're aiming for NFIT or ACB level 2. And so your spec will vary as to what your expectations are. So you might say, you know, if you're looking for a limited improvement on air tightness, you might be just looking at more conventional materials. If you're looking for ACB level 2, you'll be using specialist tapes and that sort of thing. So you will use, the spec will be appropriate to what your objectives are. And really, this same approach is valid for all sorts of levels of improvement. You really want to think of an air tightness champion. Okay, so an air tightness champion is somebody who really makes improving the air tightness their main goal. If you're doing the work, sorry, you're the air tightness champion. But if it's subcontracted, you know, if you have a contractor carrying out the work for you, somebody needs to be driving the importance for air tightness all of the time. Now that's usually, you know, if I'm talking about local builders, typical Cumbrian, you know, local builders, it's usually the owner of the business becomes your air tightness champion, because basically the contractors, the subcontractors that are working for them need to know that they're serious about it. And if they're serious about it, then they'll stick to it. If you don't have somebody who really champions the air tightness, there is quite a large risk that it won't happen. It won't happen effectively. So you want somebody who is absolutely passionate about making sure that your air tightness standard is achieved. But you need to know they need to know what your objective is, which takes you back to the first point. You've got to be really clear about it. So that individual worker responsibility. So if you're looking at achieving a good standard of air tightness, you're doing a reasonable amount of work to your property, and there's probably subcontractors around. So people need to know that it is a serious thing and they have a responsibility themselves. So if you're, you know, say the electrician who's doing some wiring, or the heating engineer needs to understand what is required, and that if something happens, they need to let somebody know. It's not a case of blaming somebody. It's just a case, look, we're all moving in the same direction, and it's, if something goes wrong, tell us. There's no point in trying to just lose it behind something. We really want to know if there's a problem, or you know, a mistake has happened, or an accident. Tell us. You know, and that's achieved through the air tightness champion and people understanding what it's all about. So things like you know, toolbox type talks, you being on site talking about the standard that's needed. It's an understanding thing. It really varies between contractors. Some have no awareness of air tightness whatsoever, and some are really well informed. You've got to work out where your contractor actually is on that scale. And I think some of the principles that are outlined in this presentation, if you start asking about those sort of things, you'll be able relatively easily to work out whether they are geared up or not. If you start talking about air permeability figures, well, what have you achieved on your last job? And they can't answer that and they look at you blankly, I think that's told you whether they're likely to be able to deliver, say, an ACB level 2 or an NFIT for you. So, you know, you are a really important part of this.
Diane, we're getting a little short of time, so if you can bring
okay, right, okay,
perfect, thank you.
Right, okay, so consider one of the problems you have is have they actually done it? Okay, is it working? So bear in mind that it's worth considering testing on completion of the air tightness layer, because you'll know if you've achieved your target, and also at that point it's relatively easy to rectify. So the images I've got on here are on a house that I tested a couple of weeks ago, which was a test at this particular stage, and we're using the images to help the householder who's doing the work themselves to go round and rectify the issues found in that test. Okay, so that's really just recapping on those items. I think the last thing I'd just like to raise is it isn't just about air tightness. Okay, what we've got here is a property that was, when it was tested initially, came in at about 20. With the retrofit works, it dropped to between 4 and 5. We're talking air permeability. I think we're talking air I might have to check that, rather than air change rate. I think we're talking air permeabilities. So a massive improvement. But the thing was that they were using the ventilation that they were using, which was primarily driven by what was in the bathroom, was really an issue from a couple of points of view. One was that it had been fitted incorrectly to start off with and set incorrectly. And the second thing was it had this really fine filter in it that just clogged up so easily. So don't think airtightness is everything. You've got to think about how you're going to ventilate the building and what you're ventilating it with. Okay, so you have to think of it on a much wider basis. You cannot just look at airtightness on its own. Okay, so this is me. These are my contact details. As Tina mentioned, I'm in Kendal, right? So I'm in Cumbria, but I also am working with people elsewhere in the country who deliver these tests elsewhere. It's not under Green Footsteps. It's under Home Energy Doctor, but it's the same test. Okay, so that's for those of you that are outside the northwest of England, and that is me. Okay.
Thank you so much, Diane. I will just try and share. Well, don't need to share my screen. We're on to the Q&A. So thank you for that talk. That just gave us some really brilliant insight into airtightness and the different properties, and quite an in-depth tour through quite a lot of material. So now we have got some questions in the Q&A, and we've got actually one. I'll tackle the first. What were the numbers for the best house? Some Debbie missed the numbers for the best house in that set of 5 that we were.
Oh, in the set of 5?
Yeah.
Yes. So the numbers are, I'm just going to go back through my notes and make sure I give you accurate information. Okay, so the best house, which was that brick one, came in at an air permeability of 5.6.
Okay. That's great, thank you. So I've got a couple of questions here. Do feel free to put in some more. I'm going to start with the simple one. Does lime wash stop air ingress?
That's an interesting one. I think I would have to say probably not that effectively. I don't actually know the answer to that. What you find with when you're looking at plasters is that the thickness of the plaster dictates how airtight it actually is. So sort of translating that to lime wash is really quite thin. So it would have some impact, but not. I wouldn't have thought it was airtight, but I can't categorically give a clear answer on that. But I would draw parallels with the thickness of plaster.
Yeah. That's great, thank you. Now we have another question, a set of questions from Richard, which is, I think this is a great set of questions because it actually illustrates the interaction between airtightness and insulation and pulls it all together. So it's quite an involved question, but I'll read out all the different sections of it. So Richard's asking about a house that's got ground floor joists with 20% moisture content. There's a damp proof course and ventilation seems to be okay. The air in the cellar is 80 to 90% relative humidity, and the subsoil has no concrete base, it's just soil. And he's interested in knowing if the lack of concrete on the ground in the cellar is could be the problem there with causing that high level of relative humidity in the cellar. But he's also added, wood boring weevils have infested due to the high moisture content, and he's wondering if a membrane under the insulation / joists underneath would allow the drying of the joist. Now, you mentioned there, Richard, of insulation membrane under insulation joists. So does that mean the joists have already got insulation or not? It might be worth bringing Richard in there to just give us a bit of information on whether we're talking about an area that's got insulation already or not.
I think the thing to I don't mean to sort of side, but we're sort of talking about airtightness. This presentation is about airtightness rather than there's quite a lot of different issues in there. And you could say, you know, and there's a lot of unknowns. We don't know, for example, whether the ventilation in that underfloor space is good, and that might be a primary issue. So that's an example where it's really important to have all of the information about a particular location. And, you know, to be honest, a complex situation like that, where there is a need for professional advice.
And in fact, you would probably need someone to come and actually go into the cellar and look, and you might be looking at some kind of surveyor, some sort of a RICS surveyor, or a person like that with the professional qualifications, and they wouldn't be able to answer those questions remotely. They would actually need to go into the building, go into the cellar and see what's there in order to answer that kind of question.
Yes.
So yeah, I think that's what we can say here and now. Just see, some more questions are coming in. So Ian has just said thank you. He's got a question about the value of the special tapes and membranes for ceiling insulation, in this case under wooden subfloor in a wind-washed void. So I don't know if you could say something general about insulating a ground floor where you've got a void underneath, and what to think about with tapes and membranes, and whether they're important, essential.
Yeah, I think the thing to probably draw out of that question, I'm sort of, this presentation has been about airtightness specifically, where something you also need to bear in mind, where you've got something like a suspended floor, where it's well ventilated, you need to think about a wind tight layer as well. I spoke about thermal bypass, so the insulation being compromised by air movement either around the insulation or within the insulation, and ideally in that sort of situation you actually want, it's a sandwich of things. So you want an airtight inner layer, and you then have your insulation, and then you have a wind tight outer layer. So it's like wearing a Gore-Tex jacket basically. So you've got that insulation is then sandwiched, you're stopping air movement through it. So that's the basic principle of what you need to be thinking of in that situation, those two layers. So the wind tight layer acts as a backstop as well. It's sort of like a two-hit thing to help the air tightness layer on the inside. So there is, you know, this particular presentation is sort of the basics on air tightness, but you know, the principle of a wind tight layer is one that really needs to be adopted where you have got airflows around, you know, potentially around the insulation. So bear that in mind.
Great, thanks. So I'll just now go to another question, and that's, what is your opinion on the pulse air tightness test as an alternative to the blower door test, and particularly in terms of the lack of pressurization, and whether this is beneficial in not forcing air pathways and requiring calculations to normal conditions rather than 50 pascals? What are your thoughts on the pros and cons of the pulse test?
The pulse test, I mean, it is widely accepted that the 50 pascals, you're testing at an extreme. The disadvantage of the pulse test is you can't use it to find anything, basically. So you might know what, it will give you a result for the building, but you don't know what the problems are. That's the disadvantage with the pulse test. So you, in terms of what, you're only getting part of the picture. So that is the issue that I see with that. Okay,
that's great. I've got a hand up, so I'll just see if we can bring Charles in. Charles, did you want to, we can unmute you if you want to to ask a question. And I think this will be our last question before I just go on to wrapping up. I think that might have been a hand up in error, so I'll carry on. If you do have a question, Charles, just put it into the Q&A and we'll see if we can pick it up. But that's been a really good number. It's already there. So we have a number of cottages with single stone walls. What's the best way to increase the air tightness of these walls? So a solid wall cottage. Okay.
With what this is the question from Charles, is it?
Yes.
Okay. The walls themselves, if it's wet plaster, will be pretty reasonable. It's the junctions that you're thinking about. So when you're examining an existing building, lots of think about where the plaster isn't, and they are the areas where you will get the air ingress. So things like where you have the void between the ground floor ceiling and the first floor floorboards. That's a key leakage area that you find. Where you've got services, so things like waste pipes leaving the building. If you've got soil pipes leaving the building, we're talking about that sort of thing. So if you think of the principle of where isn't there plaster, where is the plaster missing or broken, that will actually lead you to lots of those locations.
And hopefully these cottages haven't been done up in a way with dot and dab plasterboard at some point in the past, because that would be a different story.
It would be a different. I'm assuming they're wet plaster, Charles.
I'd like to say a huge thank you to you, Diane, for answering the questions, and to everyone who's put a question to us, because that's what gives us interesting questions and interesting things to think about. So I will just very quickly reshare my screen. And if that'll take a moment to come through, hopefully everyone can see that as it comes up. So if you've got more questions that come to mind and after the webinar, then it might be, if it's about insulation or ventilation, then it could be covered in our forthcoming webinars, or potentially, if you've got a very specific question to about your house, you could ask CAFs. We do have short advice calls and retrofit consultations by phone, which tend to be generic. We can't go into huge detail if we haven't seen the house. And again, we have other energy services where we do visit the home and we can give more advice. We have our future webinars next Thursday on insulation and the following Thursday on ventilation. And again, book on in the same way that you've done today. And also you can see all of our recorded webinars here. And from this session and previous sessions going back considerable time. And as I mentioned before, our Facebook group, Cumbria Green Build, where you'll find other people who are interested in retrofit and other green building things there. For me, it just remains to say thank you for attending. Thank you for your questions. Thank you to Diane, and hopefully see you next time or another time in the near future.